Hello, everyone.
Hi,
Yes,
Biz.
can you hear me?
Yeah.
Okay, thank you. My voice is half broken and half okay. So when I try to talk, half of the sound comes out and the other half stays silent. So if you don't understand anything when I talk, please stop me and I will repeat myself. Okay?
Okay.
So initially I was thinking of start doing review for the final exam. Hi Archie. I also miss you guys in class, but I think it's better to do it online since I cough a lot and I'm talking with a very low voice. So here online I can talk with low voice. If I try to talk a little louder, then I can stop my cough. And from my voice you can hear that it's very hoarse and it's hard to talk loudly. Thank you, Arjun. It happened to me before once, a few years ago. I coughed for 2 months to 4 months. I forgot how long. And then I went to the doctor. I mean, I went to many doctors. And then at the end, they found my problem. It was acid. Um, so first they thought it was cold. They gave me cold medicine. It didn't go away. And then they thought it's allergy. So they gave me allergy medicine. But my cough still wasn't hit. And then finally they realized it's acid reflux. So they gave me acid medicine. And then finally it went away. So it took me 2 to 4 months. And at that time, I strained my voice. And they told me one of the vocal cord isn't working. And this time, it's same thing. I coughed badly in the last 2 weeks, but I strained my voice again. So it's hard to talk little loudly, especially if I talk longer loudly. Like at the end, my voice doesn't produce any sound anymore. So this week we're going to have online class, and next week Monday we'll have our last class, and that definitely will be in person, inshallah. Means if God wills. So today and Wednesday we'll have online. Today we're going to do chapter 5, and Wednesday and next week Monday we're going to have a review. Also, if you need my extra help, send me an email. We can set up a meeting online and I can help you online. Did you guys understand what I said? Was it clear? Yeah?
Yeah.
Okay, thank you. Anytime you don't understand anything, please tell me. Otherwise, it will be hard for you what I'm saying to understand, and then you will misunderstand me, and then you may be in trouble. About your exam, I'm actually grading 130 exams because I gave exam to all of my classes. So it's around 130 students. So that's why it's taking longer because I'm grading everyone's exam together. So I grade page by page. So for you guys, I graded 4 pages. So I still have 2 more pages left for everyone. So once I'm done grading, I will post the grade online, and also I'll post the solution. And even though I said I was planning to have a review. I was planning to start doing review from today, but then I realized I didn't do chapter 5, and it's not a bad section. It's actually interesting section. So we are going to do chapter 5 today, and then 2 classes we are going to do review, plus extra help out to you if you need any help. And also to my 7 o'clock students, I sent an email. Please reply to that email. I asked if you guys can take that final exam on 17th at 5:20. So send me an email saying yes or no. Okay. And for my 5:30 class, our final exam will be next week, Wednesday, December 17th at 5:20 p.m. Now, before we start this chapter 5, does anybody have any question on 17th, right, Origin? Okay, thank you. Yes, Brandon. Next week, Wednesday, we have final, not this Wednesday, next week, Wednesday at 5:20. We have our final exam. I should write it down. I'll send out an email about it. But let me write down here. Final exam 17 at 5:20. Uh, the review is actually exam 1 and exam 2 review. Oh, and one more page on chapter 4, 5, 6. And I'm going to post that one more page after tonight, after we are done with chapter 5. Then we don't have to submit any review homework. You just have to study and definitely try those questions in the extra 1 page because they are helpful. Plus the final exam, most questions will be from 4, 5, 6, and then like 1/3 will be from 1/3 or 1/2, something like that, will be from chapter 4, 5, 6. And then the rest 2/3 or 1/2 part will be from chapter 1, exam 1 and exam 2 materials. And I also noticed exam 2 wasn't good for most of the students. Like most of you guys left the exam blank in the middle, which I didn't grade yet. So you cannot run away from chapter 2 materials. So in chapter 2, exam 2 materials. So most part in final exam, or maybe I should say 1/3. 1/3 from chapter 4, 5, 6. 1/3 of the material from exam 2, and 1/3 of the material will be from exam 1 materials. So study the review sheets for exam 1 and 2, and I'm going to post 1 page review for 4, 5, 6. Elvin, if you're kind enough, please do this and send it to me. So I'll post in this class as the solution. Did you guys notice Elvin always does everything in details? So all the solutions you see, all the homework and exam reviews actually come from Elvin. Thank you, Elvin, for your detailed solution. Yeah, no problem. Okay, now chapter 5. Chapter 5 talks about orthogonality. But before we go for orthogonality, we need to know the dot product or the scalar product of vectors. So in general, orthogonal means two vectors, they are orthogonal. Orthogonal means they're perpendicular. Okay. So two vectors are orthogonal or perpendicular if their scalar product or the dot product is 0. Means if you multiply the two vectors and the result is 0, then they are orthogonal. So what is that dot product or scalar product I'm talking about? In the dot product or scalar product, we just multiply two vectors element wise. For example, if you have vector x and vector y, they're column vector. So in order to multiply them, you need to transpose one of them. So we do x transpose y. So one of them becomes row vector and the other becomes column vector. So if we have elements, you have to have the same number of elements in both vectors. So when you just multiply row and column. So the first element, multiply them, plus second element, multiply them, plus the third element, multiply them. In other words, basically you are multiplying each element on each position and then add them. The result is supposed to be a constant. The result will not be a vector. It will be just a number. And that number is the dot product or the scalar product of the two vectors. For example, here, if our x vector is 3, -2, 1, and our y vector is 4, 3, 2, then their dot product is 4 times 3 plus -2 times 3 plus 1 times 2. So 8. And if this number is 0, then the two vectors you just multiplied, they're orthogonal, means they intersect with a 90-degree angle. Now vectors in R2 and R3, they can be represented by directed line segments. Given a vector x in either R2 or R3, its Euclidean length can be defined in terms of the scalar product. So if you want to know norm of a vector, so the norm means the length of the vector. So you have one vector and how long is that vector? To find the length of this vector, we do their scalar product under the square root. So you multiply each component twice and add them. At the end, the sum, you add the square root of that. So for example, let's say we have 1, 2 in R2, and you want to know how much is the length of 1, 2. It means if this is 1 and this is 2, from 0, 0 to 1, 2, how much is the distance? So you do 1 times 1, 1 squared, plus 2 times 2, 2 squared, and then take the square root. We have to take the square root because we are taking the length of one vector. But if you want to find the dot product of two vectors, we don't take the square root. We only take their dot product. So distance is the dot product by the square root of the dot product. So you get 1 square is 1, 4 square is 2 square is 4. So the distance between 0, 0 and 1, 2 means the length of this vector is square root of 5. So distance and dot product, they're almost similar. Dot product doesn't have square root, but distance has a square root. And distance means is the norm of the vector, means the length of the vector. Now, first thing we're going to do is we want to find the angle between two vectors. So when you have two vectors, let's say one vector is here and the other vector is here, we want to know how much is the length, how much is the angle between these two vectors. So we have two scenarios. Either the two vectors we have, they are different from one another. So they do have some visible angle between them. Or you have the two vectors, they are same vectors. One is just smaller, one is larger. So in that case, the length, not the length, sorry, the angle between the two vectors will be 0. The angle will represent by theta. So if the angle between two vectors is 0, it means the two vectors we have, they're the same vectors. I mean, same vector in two different numbers. And if theta is not 0, that means the two vectors you have, they're different from one another. So we want to know what is the length between them. So there is a theorem which states about this angle between vectors. If x and y are two non-zero vectors in either R2 or R3, and theta is the angle between them, then their dot product x transpose y is the norm of the x times norm of the y times cosine of the angle between them. So from this theorem, we can find out what is the angle in terms of equation. So if you divide both sides by the norm of the x and norm of the y, then we get cosine of the angle theta is x transpose y divided by norm of the x times norm of the y. And now to solve for theta, we need to apply the cosine inverse function on both sides. Cosine inverse. So cosine inverse and cosine cancel out. We get the theta as cosine inverse of x transpose y, means the dot product between x and y divided by the product of the norm of the x and norm of the y. So if you are given any two vectors, all you have to do is on the numerator, find their dot product, and on the denominator, multiply by the length of each vector, and then apply cosine inverse using a calculator. And then they will tell you what's the angle between the two vectors you have. If x and y are non-zero vectors, then we can specify their direction by forming an unit vectors. So from x, we can make an unit vector u, which is the vector x divided by the norm of the x. Means if you have 1, 2, 3, you are dividing this vector by the norm of 1, 2, 3, which is 1 square plus 2 square plus 3 square under the radical. Whatever you get, that will be an unit vector. And for y, you can do the same thing. Well, let's say you have another vector 4, 5, 6. To find its unit vector, you divide the vector. Sorry, divide means 1 over. You divide the vector by the norm of 4, 5, 6, which is 4 square plus 5 square plus 6 square under the square root. So 1 over that, you divide each element by that. Is this that? Whatever you get, That's the unit vector. Unit vector has the length of 1. And then if you do that, then this formula becomes unit vector of the x times unit vector of the y. And then you apply the cosine inverse on both sides. So you can find angle many different ways. This is one way of finding the angle, and this is another way of finding the angle. It's up to you, whichever method you want to use. Now let's do one example. Find the angle between the two vectors. X is 2, 3, 2, 1, 3, and y is the vector 6, 3, 9. We want to know what's the angle between them. So the angle between them, the formula says cosine inverse of their dot product divided by norm of each vector. You multiply them. So to find the dot product, you multiply them element wise. This is what x transpose y means. You are multiplying them element wise. So 6 times 2, before I to do cosine inverse, 6 times 2 is 12, plus 3 times 1 is 3, plus 3 times 9 is 27. That's the numerator. Now denominator, let's find the norm here separately. Norm of x means square root of 2 square plus 1 square plus 3 square. So I get 4 plus 1 plus 9, which is square root of 14. So norm of x is square root of 14. And similarly, we find norm of y. Norm of y is square root of 6 square plus 3 square plus 9 square. So we get 36 plus 9 plus 81 under the square root. And when you add them, 81 and 9 gives us 90. 90 plus 36, 126. So norm of y is square root of 126. So you go to the calculator and find what is cosine inverse of that. So we have 27 plus 3 is 30, 40, 42. We have 42 divided by square root of 14 and 126. Now, if your calculator doesn't have a divisions, like division this way, then you have to do cosine and then cosine inverse. Different calculators have them differently. So it depends on your calculator, what type of calculator you have. So in this calculator, the one I have to click on that trigonometry, and it doesn't have cosine inverse. Since it doesn't have cosine inverse, so I have to do cosine. No, it doesn't work. So cosine inverse has another name. It's called arc cosine. Arc cosine. Sorry. Cosine. So look at your calculator and see if your calculator have arc cosine. If it doesn't, then it will have something with cosine inverse. So since the computer's calculator is not advanced, so I don't even know how to find it here. Cosine. I don't know. So the actual calculator is way different than this calculator. this computer calculator. So you find our cosine and you put this in, then the result will be, let me see. I already have this worked out. Oh, the result is 213,639. It's 1. Cosine inverse of 1, and cosine inverse of 1 is 0 degree. So you may wonder, like, why it's 0 degree, or what does it mean? Since the angle between x and y is 0 degree, they're telling you that x vector and the y vector, they are actually same vector. And it is true, because observe the relationship between x and y. If you multiply x by 3, you get the y vector. So y vector is just 3 times longer than the x vector. So they don't have any angle between them. That's why the angle between them is 0 degree. Oh, and when you put this in the calculator, make sure you have this in degree mode. Because the scientific calculator, the physical one, they have 2 mode. One is degree and one is radian. So you have to put this in degree mode, not radian mode. Okay. So one of this question will be in the final exam. Find the angle between two vectors. Any question on this? No question. Okay. So any vectors in R2 and R3 are orthogonal if their dot product is 0. For example, if you have vectors -4, 6 and 3, 2, their dot product here is -4 times 3 is -12 plus 6 times 2 is +12 equals 0. So their dot product is 0, so they're orthogonal in R2. If you have two vectors in R3, 2, -3, 1, and 1, 1, 1, look at their dot product. 2 times 1 is 2, -3 times 1 is -3, and 1 times 1 is 1. So their product is 0. So since their product is 0, so they're orthogonal in R3. Means the two vectors you have, they're intersecting with a 90-degree angle. And then so see here the angle. If you find, so you can find the orthogonal two different ways. One is just looking at their that product. If it's 0, it's automatically orthogonal. And if you forget that, then you can just find the angle between them using the formula. See the formula here we have. So if the formula gives you 90 degree, that means they are orthogonal. So the angle, either find the angle and see if it's 90 degree or not, or find the dot product and see if the dot product is 0 or not. If 90 degree angle you have, or the dot product is 0, then the two vectors you have, they are orthogonal. So 2 ways you can verify that in a projection. So let's say we have one vector is x and the other vector is y. The projection means if you put a light here on top of the x vector, how much it occupies of the y vector, or how this x vector turns into the y vector if you put light on the x vector, that's the projection. So there are two types of projection. One is scalar projection and one is vector projection. The scalar projection means how much, what's the length of the projection you have of the x onto the y. So if you put a light on x, how much of it takes from the y vector. That's a scalar projection. It means you're looking for the length of your projection, the scalar length. On the other hand, the vector projection is asking to find a vector. What vector you get what vector you get on y if you if you try to project x onto y. What's the vector you get? Not the length. What's the actual vector you get? That's the vector projection. The scalar projection can be used to find the component of one vector in the direction of another. The scalar projection of x onto y tells us how far x extends in the direction of y. It means it's a single number scalar. It measures the length of the shadow of x onto y. It can be positive, negative, or zero. It's positive means you have the same length as y. It's negative means you have the opposite length as y. And zero means the projection and the y vector, they are perpendicular to one another. And to find this scalar amount, the length, this is the formula we use. The formula says take the dot product of the two vectors, x and y, and divide that by the norm of the y vector. That's how much you take up of the space from y if you try to see the projection of the x onto y. Sometimes we can use the unit vector, which is, many people use unit vector to find this line. And to find this unit vector, you take the vector y and divide that by the norm of the y. Like this, like the thing I said before here. The unit vector is a vector divided by its length, its norm. And to find the vector projection, you do, so let's say you're projecting x onto y. So we write project or proj, and then the subscript is y, and superscript, not superscript, like the argument is x. So we said the projection of the y vector onto, the projection of the x vector onto the y vector. This is how we read it. The projection of the x vector onto the y vector, which is represented by small p, is the scalar projection times the unit vector of y. So you can use this formula, or you can write the scalar vector, which is the norm of x and the dot product of x and y divided by norm of y times the y vector divided by norm of y. So this is another formula. Now if you observe this formula, you have the same thing twice on the denominator. So basically you have norm of y square. But remember, norm of y means square root of the sum of the each component square. So if you take the square root of a square, they cancel out, and you have each element square, sum of each element square, which is nothing but the dot product of the same two vectors. Okay, so the easiest formula for the projection vector is dot product of x and y on the top dot product of the y vector on the bottom, whatever result you get, you multiply the y vector by the result. And whatever you get, that's the projection vector. For example, let's say we have a vector 2, 1, 3 and another vector 6, 3, 9. We want to see if we project the first vector onto the second vector, what's the scalar projection and what's the vector projection for that. So the scalar projection says, scalar projection. Scalar projection says you take their dot product divided by, oh sorry, I don't have X and Y. I have V and W. So we are projecting V onto W. So V transpose W. And since we are projecting onto W, so we are going to divide by the norm of the W vector. That's going to give us the scalar projection. So B transpose W means you are multiplying them element wise. So 6 times 2, 12, plus 1 times 3 is 3, plus 3 times 9 is 27. That goes on the top. And you divide by the norm of the W vector, which is square root of 6 square plus 3 square plus 9 square. So we get, we did it before, I think. 12, 3, 27. Yeah. So it's 42, 126. 42 over square root of 126. So you go to the calculator and find out how much is this. 42 divided by 126 square root 3.742 or 3.7 since I don't have space. So that's the scalar projection. But you can actually simplify it without decimal, because 42, 126 is reducible. So you can, even though you don't know, but 126 is actually square root of 14, if I'm not wrong. Let me check. Reduce it more, whatever. I don't have the answer. So that's the scalar projection. Means the projection of the V onto W, the length of that projection is 3.7. Next thing it asks us to find is the vector projection. So vector projection of V to W. So the way you write is P as projection. We are projecting V onto W. Okay, so V onto W. So we have to have W in the denominator. So the formula says dot product on the top. So V transpose W, and then W transpose W, and then we are multiplying by the vector W. Okay, that's the vector projection. So observe, everything is the denominator. Whatever we are projecting onto, that gets the priority. So we have W here, W on the denominator, and you're multiplying with the vector, the W. So everything is W except one thing. Whatever we are projecting, that goes on the top. So projecting V transpose W, and then the rest is whatever we are projecting onto. So B transpose W, we already did this here. So this is 42. Now W transpose W, it's if you don't know what is this, it means you have 639, 639. So you're multiplying the same vector twice. So basically you are doing 6 square, 3 square, 9 square without the radical symbol. And then our W vector is 6, 3, 9. So this is W transpose W. So it should be the other way around. The row should be here and the column should be here. So I shouldn't teach you wrong thing. Let me write correctly. W transpose W means 639 row wise, 639 column wise. So we get 42 over 126. Oh no, not 126. We did it before, so let me just get the number from here. Oh yeah, it's 126, 639. So 126 on the bottom, 42 on the top, and then 639. We can reduce this. So let's see. 126 divided by 42, 3. So 1/3 of 639. So you divide each component by 3. So 6 of 1/3, 3 of 1/3, 9 of 1/3. You get 213, which is the same vector as V. Because remember, V and W, they are the same vector. So their projection vector has to be same. Our V vector is 213 and our W vector is 3 times that. So V and W. So that's why it's saying if you project V onto W, you get the V vector back because they are the same project, they're the same vector. Okay. Any questions so far? No. Now, the summary. Oh, one more thing. There's another thing. So remember, P is the projection of, so here we have projection X onto Y. So projection of X onto Y, we represent it by P. So now, let's take a look at this picture. So this is our X vector here. This is our X vector, and this entire thing is our Y vector. Now, when you project X onto Y, we get here, from here to here, we get unit vector, which is same as the scalar projection. Now, this much length is telling us that whatever we have here, this is the projection of X onto Y. Now, they want to see, so if this is the projection X onto Y, and this much length is X minus P, they want to know what's the relationship between X minus P and this projection. So are they orthogonal or they are not orthogonal? Basically, we want to know if we multiply this projection vector and this X minus P vector, do you get the result 0 or not? If you get the result 0, that means these two vectors, they are orthogonal to one another, and if they are not 0, they are not orthogonal to one another. So in the next question, it's the same question as before. Find the projection of x onto y, and also figure out this projection and x minus p, the distance from x vector to the projection. These two vectors, are they orthogonal or not? So basically you have to find two things. First, the projection vector p, and then you're going to subtract that p from x to get the distance from x vector to the p vector. So if this is your x vector and this is your p vector means the projection vector, then you want to see this x minus p and p, what's the relationship between them? Are they orthogonal or they are not? So this is x minus p. So let's do this. And here we are in R2 because we have only two components in each vector. So projection vector of x onto y is x transpose y. And then you're dividing by y transpose y. And then you're projecting onto the y vector. So x transpose y means their dot product. 3 times 1 is 3 plus 4 times 0 is 0. Now y transpose y means you're squaring each element. So 1 square plus 0 square. And we don't need to take the square root because we are not finding norm. We are just finding their transpose. Their dot product. And our y vector is 1, 0. So we have 3 over 1, 1, 0. So the projection vector is 3 times 1, 3, 0 times 3 is 0. So these are p vector. So we found this p is 3, 0. Now you want to know what is x minus p. Means what's the vector? You get the difference between the x vector and the p vector. So x vector is 3, 4. And you're subtracting the p vector 3, 0. The vector we receive is 3 minus 3, 0. 4 minus 0 is 4. So they want to know what's the relationship between x and x minus p. Are they orthogonal to one another? Means are they perpendicular to one another? So what we do x transpose x minus p. So x transpose is 3, 4 row wise, and x minus p is 0, 4 column wise. So when you multiply, we do 3 times 0, which is 0, plus 4 times 4, 16. So it's 16. So x transpose x minus p, the result is not 0. That means x and x minus p are not orthogonal. Did I make a mistake? Let me pull this. So we found 3, 0. We found 0, 4. And then, 3, 0, 0, 4. Wait, what?
We do p versus p times x minus p, not x times x minus p.
P. Oh. P and x minus p, not x. Oh man, thank you for catching that. We are observing the projection and the difference. No, not the original vector. So obviously they are not x minus p and p, they are not orthogonal, of course. So it makes sense. We are observing the p. Our p is 3, 0. So 3, 0, 0, 4, we have 0 plus 0, 0. So they are orthogonal. Means see the projection vector and the distance from the x and p vector. These two vectors are connecting one another in a 90-degree angle. And it has to be true because anytime you project something onto another thing, it has to create a 90-degree angle. Otherwise, it will not be projection. That's how projection works. They meet with a 90-degree angle. So there will be one question like this in the final exam. So find the angle between, so here, this is the summary. Find the angle between two vectors. Find the scalar projection of two vectors. Find the vector projection of two vectors. And then figure out whether these projection and the distance from the original vector of the projection are orthogonal or not. So all of these will be in the final exam. Now let me skip this. This is an example. And let me go to the next topic, which is the last topic. But before we move on to the last topic, does anybody have any question? No question. Okay. So the last topic is the closest point on a line from a point. Let's say we have a point somewhere here, point, and let's say we have a line here. Now on this line, which point on the line is the closest point from this given point? That is our goal, to find out what is this the closest point from this point, or is this, or is this, or is this, or is this? Which point on the line is the closest point from a given point? So in order to find the shortest distance from a point to a line, what we do is we first make a vector from 0, 0 to the point, and then we project that vector onto the line. When you project, we are going to have a 90-degree distance, which is the shortest distance between this point and the line. So we are going to find the vector projection, and this projection will tell us the shortest point. Okay, so if you know what is the tip of this point, so the vector projection going to tell us what is this vector, and the vector means the point we have at the tip of the vector. So basically, the given point we turn into a vector so that we can project that vector onto the line, and the vector projection going to tell us the point that is the shortest distance from this given point. That's what we are going to do. So what type of question you expect to see? This is also another final exam question. You'll be given a line and a point. So find the point on the line y equals 1/3 x that is closest to the point 1/4. So we have 1/4 here, and we have an equation y equals 1/3 x. So what you're going to do, we are going to convert this point into a vector by connecting 0, 0, by connecting 0, 0 and 1/4 with a line. So now we have a vector v. Then we are going to project the v vector onto the y. But y is a line, it's not a vector. So what you're going to do, we're going to find a vector in this line. So let's say we pick any point on this line and say, well, this is another vector we have. So we make two vectors. First vector is the point, and second vector is any point on the line. And then we project our v vector onto the vector we just created on the line, and then see what is the projection. That projection going to give us the result. So we do, let's say v is the vector 1/4. So we write it as a column vector. And then we produce another vector w, which is on the line. Basically, what we are going to do is we are substituting a number for x and get the y value. So we get a point here. So our y is 1/3 of x. Let's say x is 3. If x is 3, then our y will be 1/3 of 3. So it becomes 1. So the vector we get on the line is 3, 1. So basically we're getting 2 points, but writing them as vectors. And then we are going to project the v vector onto the w vector. So we are projecting v onto w. That means our denominator will be w, and this will be w. Okay. So the formula says the numerator gets the dot product of the both vectors. So b transpose w, and the denominator is w transpose w. So we get a scalar, a number, and then we multiply the w vector with that scalar. So our v vector, let me write them here. V is 1/4 and w is 3, 1. So when you multiply, we get 3 times 1, 3, plus 4 times 1, 4, divided by w transpose w means w, every element square in w. So 3 square plus 1 square. And then we are going to multiply the w vector, which is 3, 1. And now it's basic algebra. 3 plus 4 is 7. Then we have 9 plus 1, 10, and 3, 1. So when you multiply, we get 21, 10 divided by 7, 10. So this is the point closest to the point 1/4. And if you want, we can find the decimal. Let's see what is 7 divided by 10. 7 divided by 10, 0.6. Oh man, what am I doing? Okay, Brandon, no problem. Okay, so that's how we do finding the closest point. So basically the point here, it has a coordinate 2.1 and 0.7. So 2.1, 0.7 on the line y equals 1/3 of x is the closest point from the outside point 1/4. Okay, so that's the last topic for the final. So that's all for chapter 5. We have one more example. So let's try this last example. I mean, you go ahead, try this last example, and then we'll be done with the syllabus. So in our next 2 classes, we are going to start reviewing from the beginning. So since we already did all of this, so this memory is fresh. So we're not going to touch this until the last day. So in our next class, I'm going to go over review sheet 1. And if you have time, then start review sheet 2. And then in our last class, Monday, which will be in person, I'm going to do review sheet 2 or going over exam 2. Actually, going over exam 2 is better. I'm going to go over exam 2 or review sheet 2 and then briefly explain again what we did in chapter 4, 5, 6. So I will post a review sheet on 4, 5, 6, which is not mandatory to do, but definitely try them on your own. And then I'm going to post solution once Elvin give me the solution, if he has time. Okay. Otherwise, I have to create the solution myself. Do you make the final? Good news. This time I will make the final. Not every semester we do that. I don't know why, but this semester they told us that we have to make our own final. In some semester department does, in some semester we do. So this semester I will make our own final. So it's a good thing. I know what will be the final. So I'll tell you exactly what will be the final. All you have to do is remember your materials until the final exam. After the final exam, you can forget them if you don't need them. So Shikila, our final exam is next week, Wednesday, which is December 17th. And it will start from 5:20 to 7:20 p.m. Next week, Wednesday. Not this Wednesday. And this Wednesday, we're going to have an online class, okay? But next Monday, inshallah, definitely, we're going to have in-person class. And I'm going to return your exam at that time.
Just to confirm, the final exam, it's going to be in the same classroom we usually hold our class, right? Okay.
During the same time, just 10 minutes before our usual class time.
All right. Thank you.
Any other question before we leave? That's all for today. So if you have any question, I will discuss that. Otherwise, we are going to leave. Thank you, Gregory. And if any of you need any extra help from me, please do email me. I will help you for the Zoom. Thank you, Elvin. Thank you, Elsa. Thank you, everyone.
Thank you. Have a good night.
You too.
Good night, miss.
Remember,
Feel better.
Wednesday also online, okay? And then next Monday, we'll be in person. Thank you, Gibran. Hi, Loon, Shibu. Thank you, everyone. Have a good night.